Hello everyone, in this lecture we're going to discuss MIPS memory organization. So if we take a look at a typical computing system, you notice that you have a hard disk. Now a hard disk can be mechanical or solid state. We have RAM and we have cache, and we have can have multiple levels. We have L1 cache, L2, L3, L4. So a typical question will be, why do we design computer memory this way? Why don't we have a super fast cache? Why do we need a hard disk, a RAM, and a cache? We can think of a cache as the program memory and data memory we saw earlier inside the MIPS processor. So first, caches are extremely expensive for small data. So if you can take a look at the hierarchy here, hard disks nowadays are like 1 terabyte or 2 terabytes in size. RAM can go from 8 gigabytes all the way to 64 gigabytes, and caches we have 4 megabytes, 8 megabytes, 12 megabytes, and increasing. So you see there's a difference in sizes between one layer and the other. So if you look at the hard disk, it's typically $120, for example. For the RAM, it's slightly greater. We're looking at for example 16 gigabytes for around $100. This is for DDR4 RAM technology. For the caches, of course, the price increases extremely as we upgrade our CPU. So we can see that the price changes differently. So of course we cannot have a 1 terabyte RAM. This will cost too much. And of course we cannot have a 1 terabyte cache. This does not make any sense cost-wise. And if you look at the speeds, so as we go up there, the speed is increasing. So hard disks are typically slower than RAM. RAM is typically slower than caches. And if the price will drop like this. So this is the amount of dollars you pay per megabyte. So as we go up, the speed increases. As we go down, the price decreases. So why do we need 3 layers of memory? So this comes to the principle of locality, which states that in any memory system, the program usually accesses, so let me write this, the program accesses a small portion of its address space at any given time. So if I can break the principle of locality into 2 compartments, I can break it like this. We have temporal locality and we have spatial locality. So if I have a program, okay, let's say Microsoft Word or whatever, and I double click it to run, I don't have to place all the program in the cache to run it. The CPU will only handle one instruction at a time if it's a single core, or it can handle multiple instructions, but they are few. It's not like they're gonna access all the program at the same time. So temporal locality means that if there is an instruction that I have accessed, it's most probably I will access it in the near future. And this is true in loops. So when we have a loop, and it's repeating 1,000 times, this means those 4 instructions are going to be accessed more often than the rest of the program. And on another hand, spatial locality indicates that if I execute instruction 1, it's most probably that I will execute instruction 2, which is directly next to it. So a block of memory will be all what I need for the program to run fast. So the principle of locality is the main purpose behind this hierarchy of cache, RAM, and hard disk. And what makes it work is the fact of the way the program runs. So temporal locality, we have many loops, they are repeating more and more again, and we have instructions that are sequentially being executed one after the other. Of course, we have jumps, we have big jumps, small jumps, but this does not give the reason to have extremely large cache as we see as we go through this course. So given this, and given that we need hard disk, RAM, and cache, we're going to discuss the relationship between them, but first we need to discuss some terminology. So the first terminology I'm gonna introduce is what's a block. So we know we have an instruction is usually a word in memory. So now we're going to introduce a block, which is the minimum amount of information transferred from memory to upper layers. So if I take a look at this, let's take a memory. When we say memory, I mean the RAM. So we have the program here and we have the cache. So of course, the minimum amount of information is called a block. A block can have one or more words. Okay, remember that the CPU will access, since the value in the cache, assume we have just one level of cache, and to execute the program first resides on the hard disk, right? So I double click it, the program now is in the RAM, the cache, the CPU asks for this program some instructions to execute so that you can see the output on your monitor. So it asks for a block of information to be delivered to the cache so that it can execute those instructions and those data. Okay, so a block is the minimum amount of information that I can deliver from the RAM to the cache. Now, what happens if I didn't find the accessed words inside the cache? So here I have the notation of hit and miss. So it's a hit if the requested block or word is found in upper levels. So a hit in cache is if I find if I find it in cache. A hit in RAM is I find it in RAM. A miss if the requested block or word is not found in memory, in the upper level. So always when I'm cache, this is the upper level, this is the lower level. So if I'm in RAM, a miss in RAM is a miss inside this data memory. So the hit ratio now is percentage of hits in upper levels, and miss rate is the percentage of or rate of memory of requests not found in upper level. Of course, hit ratio is equal to 1 minus miss rate. Alright, so this is the main, these are main terminologies that we need to know them. Also, we have the concept of miss penalty and hit time. So I'm going to start with hit time. So the hit time is the amount of time we spend searching and finding the requested data. So this is the amount of time needed to search and find the requested data in upper level. Now, miss penalty is the amount of time it takes to search for the requested data plus the time it takes to get the data from the lower level to the upper level. So let me rephrase that again. Miss penalty happens when I don't find anything in my upper level. Let's say I search for a word in the cache or a block, I didn't find it, so I have to go to the lower level to find it there. If I find it there, I'm gonna transfer this block to the cache and plus the time I need to read the value to the CPU. So it takes as follows: time to replace a block in upper level with the corresponding block from lower level plus time to deliver the block. Of course, since we're accessing a lower level and RAM is much slower than cache, miss penalty is much bigger than hit time. Okay, so miss penalty is much bigger than hit time. For example, the CPU misses is around so CPU hit time is 1 to 2 cycles. The time to access the RAM will be in the hundreds of cycles. The time to access the hard disk will be around millions of cycles. So you see the speed of each component differs from one level to the other, and the speed up is huge. So now that we established the need for this hierarchy, cache, RAM, and hard disk, we're gonna focus now on cache designs. So let's talk about cache design. So we have the memory, which we mean by the RAM, and we have a single cache. Okay, and we have here the CPU, which will be reading and writing from the cache. So now, what's the best way and the simplest way to have that, to add data from memory to the cache? Remember that RAM or the memory is much greater in size for the cache. So this is in terms of sizes. So let's take a very simple approach. Let's say we have a one word block. So this means I just need to read one word at a time. Assume RAM has 32 blocks. This means 32 words. Okay, so this is 0 to 31. So a typical approach, and of course the cache has 8 blocks, which means since we have one word block, 8 words. So the simplest approach is actually, let me write 0 to 7. The simplest approach is to get this word, place 0 in 0, 1 in 1, 2 in 2, but what happens when I reach 7? The cache is full. What about 8? 8 should fill again from 0, 9 from 1, so this will go from 0 to 7 in cache, and then will be this 0 to 7 in cache again. So this is called direct mapped cache, where each block has a specific place in cache, each block in memory. Okay, so block 0 will go to 0, block 2 to block 8 will be 0. So what about block 22? How can I know block 22? It's very easy. There is a mathematical formulation. So location, say block location in cache is equal block address in memory modulo number of blocks in cache. So number of blocks in cache in our case is equal 8. So I gave the example of, let me write it here, 22, which block in cache. So simply I just say cache address, cache block address is equal 22 modulo 8, and this will be of course equal to 6. Why? Because remember, it's multiples of 8. So if I tell you what's 16, 16 modulo 8 will be 0. So we can actually know beforehand each block and its specific location in cache. Remember, this is the block address in RAM, and this is the cache address. Okay, so it's very simple and very fast because I don't have to search. There's no principle of searching here as in other caches that we'll see next lecture. So it's very popular and very fast to be next to the L1 cache. So a major question now arises is how can I differentiate between 0 and 8? Both of them will go to location 0 since they are multiples of 8. How can I differentiate between them? How can I deal with them? This is what we're going to discuss next. So if I take a look at the cache addresses, so the cache, as we said, goes from 0 to 7. This means the address is only 3 bits. Okay, the location here is one block which has one word. Okay, the main memory is 5 bits address since I'm going from 0 to 31. So as I said, block 0 will go to, this is memory address, this is cache address, will go to cache address 0, 1 will go to 1, 8 will go to 0, 16 will go to 0, and every multiple of 8, 24 will go to 0, and we don't have greater because we only have 31 addresses. So how can I differentiate between those 4 locations? So I've taken a look at the 5 bits of memory addresses. So 0 will be actually, okay, 8 will be, 16 will be, 24 will be. So if I can notice something is that I can break the address actually to 3 bits, which is the address in cache, and these 2 bits which are called tag bits. So the tag bits are special bits that differentiates between the addresses of each block. So block 0 has tag bits 0, block 8 has 0, 1, block 16 has 1, 0 as tag bits. So the cache will look like something like this. Each block, this is block 0, let's say this is 32 bits, and this we have here the tag bits. So if this is 0, 1, then I know this is block 8. If this is 1, 0, then I know this block is for block 16. Okay, and this is how the processor knows, okay, I have block 16 and not block 8, because if they are the same, then each block is referencing different values. This can be X, this can be Y, so I cannot mix them together, or otherwise the program will not operate correctly. One more bit I need to discuss is called the valid bit. So I'm going to write this here. So valid bit is actually an important bit. The valid bit is a way to differentiate when the location in cache is actually empty or not. So indicate if location is empty, non-valid, or contains data. So what do we mean by empty location? Can it be all zeros? No, because 0 is actually a value. What if it has an old value which is 5 or 6 or 10? So how can I confirm that this location is valid or not? So we add another bit which is called the valid bit. So if v equals 0 implies not valid. So the data is garbage data and I can throw it out, I can overwrite it. If v equals 1, this means it's valid, and we should take care that this value is of use to me. It's not just garbage bits that is stored inside the memory. So valid bits are very important to indicate that this location is actually populated by a value from the memory and not just random bits stored in the cache. So again, valid bits indicates that the data is valid, that it contains values read from the data memory, not random bits. Tag bits differentiate different locations in the RAM that I need to read from, and I can differentiate from which value or from which address in memory they came. Now I'm gonna give an example about memory locations, and we're gonna describe what happens in the cache. Imagine we have a series of references. So again, I'm sticking with the same example, we'll change it later on. We have 8 block cache, 32 blocks in memory. We have, let's say, each block has one word. The word can be equal to 32 bits. However, the addresses, so cache address bits is equal to 3, memory address bits is equal to 5, since we have just 32. Now imagine we have the first reference. A program is running on your computer and he started to look up data from this memory to bring into the cache. So first I have this memory reference. Let's say I have memory reference 22. So if I convert it to binary, this will be 10110. Okay, this is binary. Okay, so now directly I can say which location does this address map to. Now it's easy to do it on 5 bits, but if you have 32 bits, you need a calculator to do them. So actually we have 22 modulo 8, which is equal to 6, and this is evident here. We have just 6. This is the location in cache. So is it going to be a hit or a miss? If I take a look at the cache, I'm gonna draw the cache here. Okay, so this is 0, 1, 2, 3, 4, 5, 6, and 7. So this is the cache. Each location has a valid bit and also tag bits, and this is the block. Okay, so if we start, all the valid bits are 0. So the first memory reference will have, this is all zeros. So everything in the cache has data irrelevant to us. So the first axis, I look at the location 6. It has valid bit of 0. So of course it's going to be a miss because it's not there. So this is hit or miss. So in this case, what I'm gonna do, I'm gonna bring this block, I'm gonna change this 0. Sorry, it's not this 0. I'm gonna place 1 here. Now it's valid. I'm gonna bring block number 22, and the valid bit is actually 10, or the number 2. Now let's say I have another reference, 26. So again, 26 in binary is as follows: 11010. Okay, and 26 modulo 8 is going to be 2. Okay, and I look at location 2. This is also going to be MS. Okay, so this will turn to 1. I bring the requested data from RAM and place it inside the cache. This is block 26, and we have 11 as the tag. Now let's say I have reference to 22. So 22 of course has 1100. This will be in 6, and it's going to be a hit. So if I take a look at 22, if the memory reference came and it's 22, I'm bringing a block 22. I check the cache. 22 goes to 6, so 6 is valid. I check the tag 10, similar to the tag that I have, and the block is the same because I cannot know which block it is, and we're gonna see an example like this. If I look at 26, 26 is 11010. It has 11 as tag, and it's valid, and then it's a hit. Now let's say I go ahead and bring in another one, 16. So 16 is of course 10, 0, 0, 0. Of course 16 mod 8 will be 0 and it will be a miss. And now I say, okay, I need, it's going to be the MS. I'm going to fill it 1. The tag is 10 and block 16. Then I reference block 8. Block 8 will be 0, 1. It's just to separate the bits. Okay, 0, 0, 0. So now 8 mod 8 is equal to 0. Now I request block 8, and this resides in cache location 0. I take a look at 0, I look at the valid cache, a valid bit, oh, it's valid. So this means this value is true. However, I take a look at the tag. If I notice the tag here, the tag that I'm requesting is 01. The tag that I have is 10, and we have block 16. So what happens here is going to be a miss, although both of them are requesting the same address. This will be taken and 01 will be placed instead, and instead of 16 we have block 8. So now if I have block 0 again, block 0 will actually be a miss. Now if I go ahead and address 16 again, 10, 16 mod 8 equals 0. Is it a hit or a miss? Before answering this question, I take a look at the cache. Okay, location 0, 1. The tag is 0, 1. The tag I have is 10. No, it's a miss. Why it's a miss? Because the value is block 8 and I want block 16 to be in this place. So you see the direct map, even though the cache is empty and I have empty locations inside of it, I keep on overriding in favor of simple addressing and simple techniques to find the block inside of my cache. And as we see in the next lecture, this is not an easy task to do. I'm going to shift gears into calculating the size of a cache. So we remember that the cache, we have some extra bits. We have valid bits, we have tag bits, and we have the block. Okay. So how can we compute the size of the cache? Remember, in our previous examples, the block was one word. What if I have a two-word block? This means the block now will be handling 2 words. Okay, and sometimes I have something called byte addressing. What do we mean by byte addressing? We know that here if we have a 32 bits, this means I have 4 bytes. 0, 1, 2, 3. So what if I want byte number 2 from this block? So sometimes I would locate, or I would access, so this is block, let's say this is block 0. So I have word 0, and I have word 1, and of course I have the byte. Which byte I want? So I can say, okay, I want word 0, byte number 2, or word 0, byte number 1. So I have access to bytes and to words of each block. So as we said previously, it was one block, 1 word per block. With 2 words per block, I can have multiple words. I can have 4 words, usually multiples of 2. And I can select whether I want just a word address or a byte address. So of course, byte addressing means accessing bytes inside a block of data. Word addressing means accessing words inside the block of data. Okay, so if I take a look, and this means this block now, if I have a 2-word block, I will still have 1 valid bit, make it smaller, and 1 tag bit. However, the block now is divided into 2. So if I have a word addressing, this is block 0, this is block 1, this is valid, this is tag, again I have, this is word number 0, word number 1, word number 0, word number 1. Okay, and of course, if I have word addressing, I can only access those 32 bits. However, with byte addressing, I can access individual bits in each word, in each block. So typically, when we want to calculate the size of the cache, we need to address all of these values. So if I take a look at this cache of 2 blocks, so if I have a 32, let me write this on a new page. So as I have a 32 bit address, okay, and I have m words in a block and n blocks in cache. This means, okay, I have, this is block 0, block 1, all the way to block n, and of course I will have valid bit tag, and then I have m words. So this is m0, m1, say m2, oh sorry, this is 0, 1 all the way to m-1, and of course this is n-1 because we start from 0. So in each one we have from 0 all the way to m-1 words. And if I have byte addressing, okay, this means I will divide this into 4, and I need something called a byte offset. Of course, since we have 32 bits, the byte offset is 2 because we have 4 bytes per word. Now, to calculate the size of this cache, first of all, how many blocks do we have? We have 2 power n blocks. Okay, so this 2 power n blocks, in each block we have 2 power m words. Each word is 32 bits, so times 32, and then I have the valid and the tag. So the tag bits, what's the value of the tag bits? Tag bits is actually, address is 32 bits minus n minus m minus 2. Why is it like this? This is the address, this is called the index, which is the index in the address. This is called word address, this is index or block address. This is word address in block, and this is byte offset. So the tag bits will be 32 minus n minus m minus 2 plus 1, which is the valid bit. So this is the total number of cache. The data part is just this. This is the data part. If I want just this data part, which is this part here, it will be only this. This overhead comes from the tag, and the valid is replicated in each block. Okay, so let's take an example. So let's take an example by assuming that we have a cache with 16 kilobytes of data and a 4-word block and 32-bit byte addressable cache. What's the size of cache, which means total size? Because the data portion of the cache, so this is tag, this is valid, this is tag, this is 16 kilobytes. Okay, so this 16 kilobyte is divided into 4-word block. So how many blocks do we have? If the total size is 16 kilobytes and each row is 4 word block, this means number of blocks in cache, which is unknown. We need to find n and m to solve the size equation for this formula. So the number of blocks in cache is actually 16 kilobytes over 4 word block. So if we look, 4 word block is 4 times 4 bytes, since it's 32 bits, which means 16 bytes each block. So over 16 bytes, this will be 1k, or 2 power 10 blocks. So we have from 0 all the way to 2 power 10 minus 1, or 1023. So now we have, so n is equal 10, this is 10 bits. We have m, since it is a 4 word block, 0, 1, 2, 3. M is equal to, since we have 2 power 2 is equal 4 word block. We have byte addressing, this means I have 2 bits for bytes. Implies that the total size is equal 2 power 10 times 2 power 2, which is the number of words, that each word is 32, plus 32 minus n, which is 10, minus m, which is 2, minus the offset, plus 1. This will be equal to 147 kilobits, and I can transform this to 18.4 kilobyte. So with starting with 16 kilobytes of data, the overhead is actually 2.4 kilobytes that are not used for storage. They're used for the addressing technique, which is the direct map, for the valid bit and the tag bits. So actually, when you buy a RAM chip or chip, you don't actually buy just the data. You also account for the overhead, which is in this case the valid and the tag bits. Of course, these numbers change. If we have, for example, 64 bits, then the number of offsets will be 3, and instead of 32 we have here 64 and 64, and here we have the number 3. If we just, instead of saying 32-bit byte addressable, we say 64-bit byte addressable, this will be 64 and this will be 3 again. Now, what about mapping? We saw the mapping for a single word block. What about multiple word blocks? So we're gonna take how we can map multiple words. Consider a cache with 64 blocks, block size of 16. What is the location of byte address 1200 in memory? So typically we need to do some calculation first. So if we take a look, we have a cache. Okay, let's draw this. This is the cache. It has 64 blocks, so this is block 0 till block 63, and each block has a, of course, valid tag, and it has 16 bytes. Let me write the bytes here. Bytes. So if we have 32 bits, assuming 32 bits, 16 bytes means 4 times 4. This means the block contains 4 words. Why? Because 4 words, that 4 times 4 bytes will be equal 16 bytes. So this is why I know it's 4 words. Alright, if I take a look at the memory, I don't know how big it is. However, I want to differentiate between addressing styles in the memory. So we said that the least amount of information is a block. So the block, this is, let's say this is B0, block 0, in memory, okay, contains how many words? 4 words. So this is 0, 1, 2, 3. This is block 0. Then if I take a look at block 1, I'm going to do it in a different color. We have 4, 5, 6, 7. So this will be block 1. So this is called the word, so byte address. This is called the word address. This is called the block address. But what about the byte address? So each word is 4 bytes. So effectively we have as follows. This is the byte address. So this is byte 0, byte 4, byte 8, byte 12, byte 16, byte 20, byte 24, and byte 28. And of course here we have the word number 8, which will be the start of block 2, will be byte 32. So, and of course we can continue. We have 8, 9, 10, 11, and this is block number 2. So we need, what he's giving me is byte address 1200. We want to know first which block 1200 is this address going into. So first I need to transform. So step number 1, transform byte address in memory to block address in memory. So each block is 16 bytes. So typically to do this transformation is very easy. Okay, this will be equal to 1200 seal over 16. So we just round down. So 1200 over 16 would be 75. So somewhere here we have block 75. We have 1200 byte address. If I want the word address of it, I divide it by 4 and it will be 300. Okay, so this will be word address 300. Okay, so this is the block address. Now to check where this fits, so we go ahead and say, okay, block address in cache is equal 75 mod 64 is equal to 11. This means block 11 will have the first one as block 1200. Okay, block, well actually it's going to be block 75. Block 75, which contains the byte address 1200, which is this byte. Okay, so let me elaborate more on this idea. So as we said, in memory we have somewhere, this is word, so this is word 300, 301, 302 and 303, and this is block number 75 that we found. Okay, the byte address will be, of course, 1200, 1201, 1204, 1208 and 1212. Okay, this is the byte address. So this block, this complete block, is what goes into the cache. I only needed this byte. Remember, this is byte 1200, 1201, 202, 203, 204, 205, 206, and so forth. So I just wanted this byte. However, I cannot get a single byte from memory. I need to get the whole block inside the cache. And typically, I read the block, I read the word to get the byte address I want. So if the problem was, okay, I need 1208, it will also be block 75. So for example, say, what is block address for 1022.08? So of course I do the same thing. I go ahead and divide. So I say, okay, what's the block address? Assuming I don't know, I say, okay, 1002.08 divided by 16, and I see this will be 75 point something, which will be equal to 75. So I know that the block, this is 75, and then I go block address in cache is equal 75 mod 64, which is B11. So all the words that ranges here will go into the same block, which is block 11 in cache.